see. Okay. The that
I'm sorry, I can't hear your.
do you remember how to find I?
It's I can't hear you still.
Okay, just a second. Okay, my question is chat.
No, I don't remember actually. We need to make singular points. Yeah.
Yeah, this is the idea. So let me write again the steps. The general form of I, which you will see at the seminar, is integral on modulo of z minus z0 equals I. This is the circle. From here on to find I. So step one, you have to find singular points of fz. Step choose points belong to delta, where delta has this condition. Step 3. Compute the residue of f of z in each singular point from delta. And step 4, I to I times residues computed at step 3. Okay, and in our case, This is f of z. And let you 5 minutes to find the singular points of the function f of z and to choose those points which belong to data. Okay. Did you succeed to find the singular points and to choose the points which are in there?
Yeah.
Okay. Let's see. How many singular points do we have?
How many singular points do you have?
Yes.
2.
Yes, 2 exactly. So for step 1, singular points of f of z are z1 equals 1, okay, and z2 equals -2. What is the condition of delta?
Then 5.
Okay, module of z less than 5. So have to see which points belong to delta, and you have which points to take into consideration.
1 and -2.
Yes, exactly. You have z1 and z2. So if you compute the module of z1, you see that this is the module of 1. So its 1 is less than 5. So z1 belongs to delta. And module of z2 is module of -2, which is less than 5. So z2 belongs to delta. Step 3, you have to find first points at z1 and z2. What is z1? Take a look at this function. What is z1 equals 1? So let's take a look at this function. You have to compute the limit when z goes to z1 from f of z, which is the limit when z goes to 1 from e at z of z minus 1 squared z plus 2. And you have over 0, which is infinity, and this means z1 is pole. And the order of the pole is given by this number. Okay, this number gives you the order, so it's pole of order 2. And when the limit when z goes to z2 from z, this limit z goes to -2 and z which is e at -2 over 0, which is again infinity. So it means that z2 is also a pole. And now you want to find order, but the order is given by this exponent. So it's a pole of order 1. Okay. Now you have to compute the residue. Okay, residue of f in z equals 1 and residue of f in z equals 0. And if you have z0, a pole of order n, then the residue of f of z is z equals z0 is actually, let me start the function, is 1 over n minus 1 factorial times limit when z goes to z0 from z minus z0 to the power n times f of z, and you have to compute the derivative of order n minus 1. Okay, so if you want to find the residue of f of z in z equals z1, this is actually 1 over, you know that z1 is all of order 2, so in this case n is 2, okay, and z1 is 1. So you have 2 minus 1 factorial times the limit when z goes to 1 from z minus 1 at the power 2 times f of z, which is this one, times this one. And you have to take the derivative of order 1. Okay, you have a simplification here. And after that, you get the limit when z goes to 1, because this is 1, from z plus 2. And take the derivative. So this is the limit when z goes to 1 from this one times z plus 2 minus this one times 1 over z plus 2 factorial. We replace z by 1, so we get this expression. And this is the residue. Okay, and now in 2 minutes, try to find the residue of f in z equals z2.
Could you please show the value of Z2 again? I'm sorry, I entered late and I didn't get time to write it. Thank you.
So found the residue. That's n is correct. So this is 1 over 1 minus 1 factorial times the limit when z goes to minus 2 from z minus minus 2, which is z plus 2, at n, which is 1, times e at z over z minus 1 squared times z plus 2. And you have the derivative of order 0, so you don't need to compute the derivative of this expression. You have a simplification here, and you have the limit when z goes to minus 2 from z over z minus 1 squared. And this is here minus 2 over 9. Okay, so in the end, step 4, we have that I is 2 pi I times the residue of the function in z1, which is 2e over 9, plus the residue of the function in this point. Okay, and this is it. I know that you have seen already twice this type of applications in our meetings, and also have seen at the seminar how to find the residue, but I wanted to show you one more time how to compute these residues. The idea is that starting from this week, we will use very much the residue theorem, and you will need to use this formula in almost each seminar. So this is why I insisted, and I wanted to talk again today about the residue of a function in a point. My idea now is to give you another problem which involves applying this theorem. I will let you a few minutes to solve it, then we'll talk. And if you have other questions, please tell me in that moment. Okay, because I like to answer to your questions, but now to be sure that all of you know how to compute a residue, and this is why I have to write another problem here. So let's see. Compute let's change here. Let's write step 2. Let's write 2. Oh, I will give 15 minutes at most to compute I, of course, using the residue theorem. But if you finish earlier, please tell me. Okay, so at most 15 minutes to solve this
Not yet.
5 minutes? Okay, 5 more minutes to start. Have you
I think we're having trouble with the second limit from what I've talked to my colleagues.
the second thing to check? Let's see. So you have this function which is f of z. Okay, so this is f of z. And at step 1, you had to identify the singular points of f, and they are z1 equals
-1.
okay, then z2 equals
I.
and z, which is minus I. Okay, because you have the equation z plus 1 squared times z squared plus 1 squared equals 0, and you have z plus 1 squared equals 0, or z squared plus 1 equals 0. Okay, and this is why you have the solution. Let's go to step 2. The condition of delta is this one. And let's take them separately. You have that module of -1 plus I is square root of 2, which is 1.4 and something, which is less than 3/2. So it means that z1 is in delta. Also, for z2, you have to replace z2 by I. So you have that the module of I plus I, which is the module of 2I, is 2, which is greater than 3/2. So you have that z2 is not in delta. And for z3, you have the minus I plus I equals the module of 0, which is 0, which is less than 3/2. So you have that z3 is in delta. Okay, I guess that you obtained the same results until now. And
Yes.
okay, now let's see, at step 3, what do you have to do? At step
Limit of the f of z when z tends to the values that we found.
step, you have to find what type of points do you have. So if you compute the limit when z goes to z1 from f of z, you get actually the limit when z goes to -1 from hyperbolic sine of z over z plus 1 squared times this one. So it's hyperbolic sine -1 is something which is 0 over 0 is infinity. So this one is a pole. Would you please tell me the other?
Two.
The order is 2, so I have a pole of order 2. And similarly, I get that this is infinity. So it means that z3 is a pole of order
Is it 4?
no, it's 2.
Oh, okay.
It's 2 because you have to take a look at this expression, okay? You know that z3 is a solution which belongs to this equation. So you have z squared plus 1 all squared is actually written as z minus I times z plus I. Okay, so this product is this expression, but this product must be squared from here. Okay, these two comes here. And you have that this is z minus I squared times z plus I squared. Okay, so I is a pole of order 2 and minus I also pole of order 2. But don't need I because I is not in delta. So we are just taking a look at minus I, and we see that it is a pole of order 2. Okay, from this reason.
Thank you.
Welcome. And now you have to compute the residue. The residue of f of z is z equals minus 1. It is actually the limit. I'm writing again that fraction because n is 2, so I get 1 here. And I'm writing the limit when z goes to minus 1 from z minus this value, which is actually z plus 1, the power n, but n in this case is the order, which is 2. So I have this one times the function f of z, which is hyperbolic sine of z plus 1 squared times z squared plus 1 squared. And because n is 2, I have to put the derivative. Okay, and this is the limit when z goes to minus 1 from, and let's compute the derivative. You know that the derivative of the hyperbolic sine is hyperbolic cosine. So you have this one times z squared plus 1 squared minus this one times, and the derivative of this fraction is 2 times z squared plus 1 times 2z. And simplify here. And I will get, I'm replacing by minus 1. I have hyperbolic cosine of minus 1 times, this is 1 plus 1, so this is 2. Okay, minus, I have 2 times z is actually 4z, but z is minus 1, so it's plus 4 times hyperbolic sine of minus 1 over 2 for the 3, which is minus 8. Okay, so this is the first residue. And now let's see the second residue. I have the residue of f of z in z equals minus I. Again, n is 2. So I have the limit when z goes to minus I from z minus minus I, so it's z plus I squared times this one. And now, what should I write instead of z squared plus 1 whole squared? What should I write instead of this fraction, of this expression? So I'm going
That
to
minus
use,
I times the plus I square.
yes, I'm going to use this equality. Okay. I write actually, I'm going to use this equality. So I have z minus I squared times z plus I squared. And I take the derivative of this expression. And I have multiplication here. And now I have to compute this derivative. I'll write it here. Okay. So I have the limit when z goes to minus I. From this one. I have to stop this one and steps. And now I have to compute the derivative of this like a product. So I have derivative of the first function, which is 2 times z plus 1, times the second one, which is copied, plus the first one, which is copied, times the derivative of this one, which is 2 times z minus I. Oh, I'm not trying to simplify this fraction anymore. I'm just replacing and I see what I get. So I have cosine hyperbolic of minus I times. You see here minus I plus 1 times 2. So I'm going to use this factor and this one times from the first half to I and this one. So I didn't copy properly. You have z plus, this is z plus 1 squared. Okay, sorry. So I have minus I plus 1. Okay, this and this both squared are common factors. And I have this term plus this one. Okay, over this one. And you have to make tests and see what you get. And at step 4, I will be 2 pi I times the residue of the function in minus 1 plus the residue of the function in minus I. Then questions. Do you have questions?
No.
None of you?
No, thank you.
Okay. I will give you something else. Second thing. Okay. I will let you 10 minutes to think about the solution of this problem. Of course, you have to compute E using the residue theorem. Okay, 10 minutes. Did you succeed to solve this problem? Have you finished the computations?
I got really weird values for Z1 and Z2.
Yes, I know.
Okay. But
I
how do we do
just-
the limits then?
There is no need to compute the limits because you know that Z1 and Z2 are solutions for the equation denominator equals 0. So, in the denominator, if you replace Z by Z1 or Z2, you get automatically 0.
Oh, okay.
And if you want to compute the residual, then use Z1 and Z2, not the value of Z1. Work with Z1 and Z2. Do not replace them until you get the final limit.
Okay, thank you.
Welcome. I will let you 5 more minutes and then we discuss. Have you succeeded to finish the computations?
I cannot compute the limits.
Okay, let's see. So f is 1 for plus z plus 1 squared. Okay, step. Similar points of you have that for z squared plus 1 0. So you have that delta is 1 minus 4 times this one, so 1 minus 16, so it's minus 15, okay? So you get that z1 is minus 1 plus times square root of 15 over 8, right? Because a is 4, so I have to 8. So I have to 8 here, so it is 8. And z2 is minus 1 minus I square root of 15 over 8. Now, step 2. Delta has the condition modulo of z less than 10. And we have that the modulo of z1 is the modulo of minus 1 plus I square root of 15 over 8, which actually the modulo of minus 1 plus I square root of 15 over the modulo of 8, which is 8. And this is square root of 1 plus this squared, which is 15 over 8. So we square root of 16 over 8, so it's 4 over 8. So it means that 0 belongs to that. See, this mod is modulo of minus 1 minus I square root of 15 over 8, which is square root of 16 again over 8, which is 1 over 2, which is less than 10. So z2 is in that. Okay. We have seen what type of points are z1 and z2. So we have to compute the limit when z goes to z1 from f of z, which is the limit. Do not replace z1. You know that z1 is solution for the equation denominator equals 0. So you get 1 over 0. Because if you replace z by 1 in this expression, you get 0. z1 is the solution of this equation. Okay, so you get that z1 is a pole of order, and you tell me the order.
2.
Okay, of order 2, because this expression is written as 4 times z minus z1 times z minus z2. Okay, whole square. And you have that z1 is pole of order. And similarly, 2 will be pole of order again from here. Okay. Now, let's find the residue of the function f of z in z equals z1. You have 1 times the limit when z goes to z1 from z minus z1 squared times function f, but I will write 1 over, and instead of this expression, I will write this one. So it's 16 times z minus z1 squared times z minus z2 squared. Okay, and you take the derivative of this expression. This is why you have to write expression of products to simplification. As I told you earlier, I'm going to work with Z1 and Z2 now. So I have a limit when Z goes to Z1 from, this is actually 1/16 times, and this fraction could be written as Z minus Z2 at -2, okay? So you have the limit when Z goes to Z1 from 1/16 times, and the derivative of this function is -2 times Z minus Z2 at this one -1, which is -3, times the derivative of this expression, which is obvious one. So you have -2/16 times, and I'm going to replace here Z by Z1 because I have this limit. So I have actually 1 over, and instead of Z, I have Z1 minus Z2 at this point. Okay, so this equals -8 times, and for the moment, I'm going to copy this expression. I'm not making many computations here. You'll see why. So I get this residue, this first residue is this one. Where you had difficulties? Where did you have difficulties?
For
In,
this residue, I had replaced Z1. So
No, I've told you at the
I
beginning.
thought only for the limits we have to not replace them, but for the residue we have to. Now
the
I understood.
The residue is also a limit.
Yes.
Okay, so the idea is to work with Z1 and Z2, okay, not to replace. And let's find the residue of the function f when Z is Z2. And this is the limit when Z goes to Z2. You have similar computations here. So, right, faster. Simplification. And get this one. And to replace Z by Z2, so it's -1/8 times over Z2 minus 1 cubed. And this is why I told you not to make many computations, because when you go to step 4, you get that I is 2 pi I times the sum of the residues, but the first one is -1/8 times this one, so you have Z1 minus Z2. Plus this one, which is -1/8 times so this is, but this one is minus Z1 minus Z2, so you have 1/8 times 1 over Z1 minus Z2 cubed. Okay, I take 1 from here, I put it here, and I get a plus. And this is the same with this, so I get 0, and that's all. Okay, do you see now I don't need to replace Z and Z1 because they have very, very ugly expressions, and you won't be able to solve properly and fast this problem if you are replacing what you have here. So my advice is to work with Z1 and Z2 denoted this way. And in the end, to replace them, if you don't need to replace them, compute the expression as this. Okay. Just a second. I'm going to write another example. And this will be the last example that we are discussing today. Compute which is this integral. So see the one is so compute I, this is 4. Using the residue theorem. Okay, I will let you 15 minutes, and if you have questions related to the previous problem, please tell me. If not, try to solve it in 10-15 minutes. Okay, 15 minutes. Have you finished the computations?
The residue cannot be infinite, can it?
Yes. Let's see. So you do this with step C. Step 1. Singular points of F. Z1 equals 0. Z2 equals I square root of 2 from here. Z3 equals minus I square root of 2. And Z4 equals minus 4 from step. That is this condition. Oh, sorry, 3, not 1. So, modulo of Z1 is 0 is less than 3. So Z1 is in delta. Modulo of Z2 is square root of 2, which is less than 3. So 2 is delta. Modulo of Z3 is again square root of 2, less than 3. So Z3 is in delta. And modulo of Z4 is 4, greater than 3. So Z4 is not in delta. Okay, let's see Z1, Z2, Z3. Let's move to step 3. What type of point is Z1? What type of point? Could you tell me what type of point is Z1?
Pole of order 3.
Yes. Pole of order 3. This is pole of order
2.
no 1.
Oh, it's 1. It's 1 because yeah.
Yes, because Z squared plus 2 is Z minus I square root of 2 at the power 1 times Z plus I square root of 2 at the power 1. So the order is 1. And this is pole of order 4. And in each of those, let's see the reciprocal of Z. This is the most complicated. In Z1 equals 0, in Z equals 0 actually. This is the when Z goes to 0 from, actually you have 1 over 2 in front of this limit, so I'm going to write it first. You have that n is 3, so you have 1 over 3 minus 1, so you have 1 over 2 factorial times the limit when Z goes to 1 from Z minus 0, which is Z cubed, times the function, which is 1 minus Z times e at minus Z over Z cubed times this one. Okay, and you have to compute the derivative of order 2 because n is 3. And time when Z goes to 0 from, let's first derivative have derivative of this function, which is a product. So you get minus 1 times e at minus Z plus 1 minus Z times the derivative of this one, which has a minus actually, times Z squared plus 1 times Z plus 4 minus 1 minus Z times e at minus Z times the derivative of this function, which is the derivative of the first one plus 4 plus this expression times 1. Okay, plus 1 times z plus 4 squared. But in order to obtain a simple, and you have to compute the derivative, in order to obtain simple functions, I advise you to separate this fraction to two fractions, and you'll have a simplification here. So get e at minus z times, and you have minus 1 plus z, so it is minus 2 plus z. And when you make the simplification here, you get this one over z squared plus 1 times z plus 4. Okay, this is the first fraction. Minus, got the second fraction. This is 1 minus z times e at minus z times. You have 2z squared with this one is 3z squared. You have plus 8z from here plus 1 over this one.
Will it be minus 13 over 16?
Sorry, wait.
I didn't hear, I'm sorry.
Can you repeat, please?
Will it be minus 13 over 16?
I don't know. I didn't make the computations.
Oh, okay.
So you have to compute first the derivative of this one, which is minus e at minus z times z minus 2. Okay, times z squared plus 1. It makes complicated, but z is equal to 0. You have multiple computations to do. Times this one. So you have the derivative of this one times this one. Or better, I think that I should write in brackets. Okay, I wanted to write directly, but now I want to do this. Plus e at minus z times derivative of this one, which is 1 times z squared plus 1 z plus 4. Okay, minus e at minus z minus 2 z times the derivative of this function. But the derivative of this function was computed earlier. It's this one, which is actually this one. 3z squared plus 8z plus 1 and all over z squared plus 1 squared over this one squared. Okay, so this was the first fraction. Minus, and now let's get the second fraction. The denominator will be this 4 times 4. And you have derivative of this one. If you want to compute the derivative of product of three functions, then you have to compute the derivative of each function at a time. So you have this one, which is minus 1 times e at minus z times this bracket 3z squared plus so on. Then you have plus 1 minus z times derivative of this one, which is with a minus in front of it. So you get a minus e at minus z times 3 squared plus 8z plus 1. Okay, times plus 1 minus z times 2 minus z times derivative of this one, which is 6 plus 8. So I'm taking the derivative of each function at a time, and I have this expression derivative times z squared plus 1 squared z plus 4 squared. Okay, I must write here a minus, but I want to split these fractions into two, and because I have here a minus from the formula and a minus in front of it, I get that the expression is actually minus. So I'm having to say name and to write again. I have to copy this expression. It's 1 minus z times e at minus z. Get z squared times plus 1, sorry, 1 times the derivative of this one. And you have product, so you get 2 times squared plus 1 times 2 times z plus 4 squared plus squared plus 1 squared times this one is 2 times z plus 4. Okay, over the same denominator. And let's find the limit. You have 1 over 2 times. Okay, the advantage is that z is 0, so this is 1. This is minus 1 minus 2, so this is 2 plus 1 is 3. So this is 3 here. 3 times 1 times 4. So you have 12. And so on. Minus and minus 2 is plus 2. Okay. Over, this is the first fraction, over 16. This was this long fraction. Minus, let's see the second fraction. You have minus 1 from here. Then you have minus 1 from here in a bracket. And you get 8 from here. No, yes, 8 here. 8 times. This one is 1, this one is 16. So it's 16 over 4 at the 4th. Okay, plus this one, which is 1 times 0 plus 8. Okay, over the same denominator, which is 4 at the 4th. So you get 1 over 2 times 4 minus 86 over 4 squared plus 8 over 4 times 4 cubed. So you have simplifications here. I won't make them anymore. So I hope that you get the idea. When you have f times g times h, the derivative of this one, you get actually f prime times g times h plus f times g prime times h plus f g h prime. Okay, this was the rule that was used. And two used and use RGC of function f is equals minus I square root of 2, which is actually the limit when z goes to this value from the function. You have in front of the function, but I'm going to write here z plus I square root of 2 from the formula, and then you have z squared, and then you have z I square root of 2 times z minus I square root of 2 times z plus 4. Okay, you have a simplification here, and you have to replace, and the last residue will be computed in the same manner. And at step 4, you have to make the sum of the first with the second and the third residue. I admit that the most difficult part was this one, in which you have to compute the derivative of further 2 for this function. But a lot of practice will help you to compute well the derivatives that you'll have at the final exam. So I think that this exercise really helps you to have a compute a serious derivative function. Okay, and these are the questions. Okay, if you have questions, once to download the attendance list, to see the attendance list, and we have finished. Just a second.
Teacher, if we ever get to infinite residue, it means we are wrong, right? Like, it's not
Yes.
possible. Okay,
Yes,
thank you.
yes, it's not possible. Welcome. So just a okay. Roman,
Yeah, hello, hear you.
Jacques left. Okay, Anna, can you hear me? Okay. Pico, Edward,
Sunt aici.
bine. Udrea,
Present.
okay. Andra, I have talked to you earlier. Leila,
I'm present.
okay. Ștefan,
Prezent.
Tayel,
Prezent.
okay. And that's all. Thank you very much. Do you have questions? Okay. Have a nice evening. Thank you. Bye.
Bye, thank
Thank you. Have a nice evening.
Nice evening.
Nice evening. Bye.
Bye.